In section 4.2, we started doing inference for quantitative data. We're going to use the t-distribution to compute confidence intervals and hypothesis tests for one sample means. But first, we need to know what the sampling distribution of the sample mean looks like. The first learning objective in this section is to describe the sampling distribution of the sample mean, including shape, center, and variation. Statistical theory tells us what the sampling distribution looks like. The sampling distribution is the distribution of all possible values of X bar from all possible samples of the same size that can be taken from the population. We know that the center of that distribution is equal to the center of the population. So this mu sub X bar is the notation for the mean of the sampling distribution of X bar, and that is equal to mu. The spread or variation is the standard error of X bar, and that is equal to sigma divided by the square root of n. In this example, we are told to assume that blood pressure readings are normally distributed with a mean of 117 and a standard deviation of 9.6. So this value 117 is the value for mu, and 9.6 is the value for sigma. If 144 people are randomly selected, describe the sampling distribution of X bar. 144 is our sample size. So we can compute mu sub X bar, which is just equal to mu, which is 117. And the standard error of X bar is going to be equal to 9.6 divided by the square root of 144. And we can calculate that in GeoGebra. We're going to compute 9.6 divided by the square root of 144, and that gives us 0.8. The shape of the sampling distribution of the sample mean depends on the sample size. If the sample size is above 30, then the sampling distribution of the sample mean will be approximately normal. Now, if the original population is normal, the sampling distribution will also be normal. In this case here, we are told that blood pressure readings are normally distributed, and so therefore the shape of the population will be normally distributed as well. Let's look at another example. Here's an example where the population is not normal. Suppose the circumference of regulation soccer balls is left skewed with a mean of 69 centimeters and a standard deviation of 1.5 centimeters. If a sample size of n equals 36 is taken, choose the appropriate statement about the sampling distribution of the sample mean. So we know that the mean of the sampling distribution will be equal to the mean of the population, which is 69. We know that the standard deviation of the sampling distribution of the sample mean will be equal to sigma over the square root of n. In this case, our sigma is 1.5 and our sample size is 36. So let's compute 1.5 divided by the square root of 36. And that gives us 0.25. Because the sample size of 36 is higher than 30, at least 30 is what we need for the sampling distribution to be approximately normal if the population is not normal, as this one is left skewed, we know, since 36 is at least 30, that the sampling distribution will be approximately normal. So we want the answer that tells us that we have an approximately normal sampling distribution with a mean equal to a mean equal to 69 and a standard error equal to 0.25, which is this answer here, D. And then finally, this question here, the number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate cookies is normally distributed with a mean of 1262 chips and a standard deviation of 118. Chips according to a study by the U.S. Air Force Academy. What is the shape of the sampling distribution for samples of size 49? Here, the population is normally distributed, and so therefore the sampling distribution will also be normally distributed. If the sampling distribution came from a population that was not normally distributed. For example, if the number of chocolate chips were left skewed or right skewed, or the shape was unknown, then our answer would have been D, because our sample size of 49 is at least 30. However, we don't need a sample size that large if the population is already normally distributed.